Yeah, there we go. Okay. This is a weekly live stream in which, for 1 hour, you get a front row seat into how a professional software developer goes about writing code and solving problems. I am recording this video on Thursday, April 13th, 2023. My name is Savanni, and I'm a staff engineer at 1Password. I learned to program when I was 12, and I've been a full-time developer since January of 2000. I have, in that time, been all up and down the entire software stack, from as low as individual logic gates to as high as building GUIs for GTK and for the web. Now, tonight, for the last several weeks, we have been building an application for playing Go. We are going to actually start implementing the logic for the game, like the real life thing here. But first, got to see if the GUI app is in a position to actually be demonstrated. Yeah, let's switch over to the code. Boom. Found the right button. Okay, yep, everything's okay. I'm really not a great live streamer, so sometimes the software can give me trouble. I'm just going to start the game up. I have to actually tell it which app to run. We got very close to being able to actually put stones on the board last week. The one thing that didn't happen was that I wasn't rendering that the stones had been put on the board. I worked on that actually a little bit later on in the evening and got us to, there we go, there's the app. Got us to the point where now that the stones are on the board, they actually stay there. And I've got some loops in the back that are measuring things like the rendering time. I'm actually really not happy with that. This should be down in the millisecond, maybe 5 milliseconds or so, but when I was coding this, I didn't really understand. Well, I actually still don't fully understand how Cairo works. I'm pretty sure that there are some things that I can do to optimize this whole rendering, because every single time there's a movement on the board, it is a complete re-render of the background and the grid and all of the stones, and I think I can do better. But that's not the goal for tonight. The goal for tonight is there is this actual game. Maybe the game should work. And for that matter, maybe, oh yeah, you can't actually place a stone on top of another stone. Good. I got that right. Yeah, maybe this should actually be a game. So I'm going to do this total test-driven development style tonight. And I have taken the liberty of going ahead and writing some tests. Oh yeah, I did actually commit the tests. Great. Let's start out though with the rules of the game. First of all, you've got two players. They take black and white. Each one take turns placing individual stones, and black plays first. Not always the case, but for now we're going to keep it that way and not get into the extra details. Stones are placed on the board on the intersections, the line intersections, and they are not moved once they are placed. A stone is said to have liberties, and we'll get into what that means in a moment. A stone with no liberties is removed from the board. A group of stones of the same color share their liberties. So those are actually the really big rules right there. If a stone ever runs out of liberties, you remove it from the board. And what that means actually requires going back to the game. We're going to place some stones out. Okay. Liberty counting. First of all, once a stone is on the board, every adjacent empty space is called a liberty, and it has to be an empty space. that would mean that this stone right here has 3 liberties around it. This stone, or no, oh, I am sorry. This stone that's in the middle has 4 liberties around it, just 1, 2, 3, 4. This one on the edge has 3 liberties. One in the corner has 2 liberties because it's only got 2 lines emanating from it. The edges don't count as empty space. This stone, this black stone right here that's mostly surrounded by white stones only has 1 liberty. These white stones are taking liberties away from the black stone. Similarly, this white stone right here that's completely surrounded by black stones, this one has no liberties. Diagonals do not count for liberties or for connections. A second part of this is that 2 stones linked together actually share their liberties. So having now placed this black stone, this is a group of stones. These 2 are forever linked. If they ever get removed from the board, it has to be both of them removed at once. And this group together now has 3 liberties. Actually, there's nothing else really to explain there. There are additional rules that get involved, but the point of the whole liberty count is that if you're trying to capture a group, you have to run that group out of liberties. Actually, we'll add one more condition here. Let's do this. And then we'll do that. There we go. So this is a group of 3 white stones in the corner. It's got 4 black stones around the group, but it still has 1 in liberty on the inside. And that's very important. It's all about, or that idea of having liberty on the inside is both the root of life and death. It is also the root of capturing territory for the game, which is actually your real goal. Capturing other stones is really quite secondary. So let's go back to the tests. We will run the tests there. I'm going to give us some more space. And tonight it actually is going to be side by side because I want to see the constant updates, test-driven development style. Most of these I am printing out the boards using O to represent white stones and X to represent black stones. And I've set up a couple of scenarios here. I want to focus us on the very first scenario. First, I'm going to disable that one. This one is just verifying that the show operation works. In fact, I'm actually going to remove it now that I'm done. So let's work on this one, counting an individual liberty. Let's see if I can figure out how to run just one test. It counts individual liberties. Nope. Oh, wait. I'm going to back up, get the quotes in the right place. Perfect. That's exactly what I want. We are only going to solve this one. And for this test, I have set up 3 stones out on the board that illustrate 3 of the most basic positions. And we're going to figure out how to count these. We should start out with the fact, though, that I don't have an API. Getting used to having the camera right here. Oh, also, I'm not on camera right now. Silly me. I don't currently have an API that will do the counting. It's not even that I don't have the function. I don't even have an API to call. So what I haven't decided on is exactly how to do it. I don't think I want to modify this function, but it is kind of tempting to do so. Instead, I'm going to just create a function for a group. And bearing in mind that a single individual stone is a group of 1, we actually want to find, given an address, we want to find, well, right now we're just going to stick with the 1 stone. So let's come down here. keep on printing the board, but we're going to assert that board.group at 33.map group g dot has liberties is going to be equal to sum 4. We'll do that for 3. So now for the stone at 0, 0, or at 0, 3, which is this one, should only have 3 liberties, and then the stone that is at 0, 0, up here, whoops, up here in the corner, should only have 2. And of course this shouldn't compile because the group function doesn't work, groups don't exist yet. Let's define a group. Let's see here, struct group. I'll go ahead and call out the color. And I think I will keep a list of all of the coordinates that are part of the group. Not yet. For test-driven development, we're going to do this, the minimal thing that will actually work. Let's implement the group. Pub fn liberties self I guess just U8. And we're going to make a tiny bit of the test pass by just returning 4. So we create the trivial result, which isn't as trivial. So let's see here. We're going to let stone equals self dot, no, we're going to match self.stone at column row against none. For that we return none. Some a white group and a black group. And it's not liking that because this is an, I need to be returning an optional set. Close, not quite there. Private type group in a public interface. Oh, that's easy enough to fix. That should do it. Okay, so the test that's now failing here is on line 211. That is the second one where I actually have to start doing a real count. So let's do that. How do I figure out where the board is? I think what I need to do I don't actually know how I want to do this. If I were to do the counting in group, then that means that group needs to have a reference back to the board so that it can be constantly referring to the board itself. And if I don't, maybe group is actually just a utility structure for keeping track of a bunch of stones. Let's do that. So I'm going to take the liberties function method off of here and put it on here. And I will pass a group in. And so that changes things a little bit. My API becomes board.group, grab a group, and then when we map it, what I now want to do is call board.liberties with that group. Let's see if I can actually do that. Kind of okay, maybe. Oh, that's unexpected. Okay. Map function, right. The map function consumes the original value. Okay. We're back to working. So now what we need to do is for every stone that is in the group, we need to look at all of its adjacent spaces. And we don't currently have a way to represent that there is a stone in the group. So let's add that. Okay, and now column, row, column, row. And of course this code is still incorrect, but we're gonna continue to improve it. So let's see here. We're looking at, make sure that still compiles and runs. Good, good. Now, looking at an individual stone, I want to calculate the adjacencies. That actually does belong here. And I'm going to go ahead and give it a max column and a max row. Because while I've got a lot of things hard-coded to 19 by 19, that's not guaranteed to remain the case. And I have written this many times and I don't actually remember. I don't have it lying about anywhere. So we're just going to do this again. So we're going to say column -1 by row minus, no, that's, have to keep orthogonal. And then column by row -1. So if I'm right here, this first one, we're going from here, we're going one column back over to here. For this one, from here, one row back up to there. And now let's finish it out for the other side of things. So column +1 row, and then column column row +1. Okay, so we're just going to count the adjacencies. So group.adjacencies.length. Oh yeah, self.size.width. Is that the number of columns? Yes, self.size.height. Expected U8 found U size. Width and height are U sizes. It's actually a little inconvenient that those don't convert, but I understand. length is a usize. I'm just going to stop struggling against it. Okay. And I need to add my self parameters. And I don't know, yeah, the auto formatting won't let me do that. Okay. The test should still fail, and in fact it does fail, but not for the reason that I intended it to. That's fine. It's failing because you can't subtract 1, or you can't fall below 0, and at least one of these things was subtracting 1 from 0. So I think maybe within here what I actually want to do is turn everything into like an I32 for use. No, that seems hacky. Very, very hacky. So if self.column minus 1, no, that's going to panic. If self.column is greater than 0, then we can say sum that, else none. And then it's if self.row is greater than 0, or self.row is greater than 0, we're going to do sum that tuple, else none. And let's do the same thing with these. Else none. Syntax problem. And of course now this is going to fail because the function isn't supposed to be able to return nones, or options really. So let's see. I think what I want to do is, I've got the vec into iter.filter. Actually, filter map, I think, is the method. Yes, the returned iterator yields only values for which the supplied closure returns some value. Oh, this could be kind of fun. I think I'm literally just going to return v. It did not like that. Cannot be built from an iterator over elements of type U8. That's not supposed to be what that is, though. basically I'm getting a type problem and I'm not sure why. So I'm going to comment that out and do that. It's still really angry. It's supposed to take 2. Oh! There's a little bit of syntactical complexity here. Some can only take 1 argument. So if I want to put a tuple in there, I have to do like this double parentheses thing. And then I didn't fully fix all of that. Okay, all of the syntax is now good. Awesome. Panicking is not implemented right on this line, 220. Let's see. That's looking pretty good. Oh. Well, look at that. The test now passes, which means that I am actually counting all of the liberties correctly. Let's do a quick change here, because I don't really want to hold on to the intermediate variable. Awesome. There we go. Just to fully verify, and do that. And that line of code fails because I'm saying that it should only be 1 liberty and it's calculating out 2 liberties. So this is good. We'll set that. We'll have the test passing. Great. Can I just add a second test? Stones share liberties. Yes, it ran the first test and now it's running the second one. That's great. Actually, I think I might now be at a point where I just want to be running all of... Now, I'll get through this one and then I will run all of the tests at once. Have a cup of tea here. So there is only one group in this place, and this group of 4 stones has 1, 2, 3, 4, 5, 6, 7, 8 liberties. So this 1, 2, 3, 4, 5, 6, 7, 8. Actually, we don't want to move on to this yet. There's actually still some stuff in here that I haven't done. Let's come back. Sorry for the little gotcha there. There's a couple more things. Let's go ahead and panic. No, we're just going to assert false. Okay. So I wrote some extra code to handle cases that we are not testing, and that's the cases that are out at the end of the board. I want to make sure that those are getting handled. So let's put some stones out there. This is going to be like 18, 9. So column 18, row 9. Just for the fun of it, we'll make it black. And then let's go all the way out to the last corner. Okay, so we've got those. Now we have to make sure that those are being counted correctly. And I'm actually going to make this purposely wrong for the moment. Do that. This should fail. 253. It did not fail. That's a bad sign. Okay. Okay. Awesome. Let's put some debug prints in. Let's see here. So what I know in both of these cases is that we are running off the end, and it is probably just an off by one error right here. Oh, that syntax doesn't actually work. Self.column, self.row. And in order to make sure that that the standard out appears, we need that assertion, or we need to force the test to fail, because otherwise it's just going to eat standard out. And I think because max row and max column I've set, are those 19? That's 19. That means I'm setting max row and max column incorrectly. That's the address. Don't do that. Adjacencies. Let's try that. There we go. So now line 252 is failing. This line. And it is failing because I'm saying that it will be 4 and it's supposed to return 3. Since this is the stone at 18.9 right here, it really should be 3. So let's fix that. And then the next one should fail because it should be 2 liberties, not 4. And that is, check the line number, 253. Yes, that is exactly what it's doing. And now it is asserting on the last one. There we go. Let's go back, remove that printout. Not going to need it, at least not right now. Alrighty. So now let's go back to sharing the liberties. So now what I need to do is, when I am looking at those adjacencies, I need to I need to look at all of the adjacencies for a particular stone, which means that this particular adjacencies function, again, doesn't belong here on the group. So, what do? I think I actually have to make the stone a bit smarter. Because when I ask for a stone, I get just a color. What I actually need to start doing is, let's create a new structure. Pub struct stone. I'm going to give it its address and its color. And then these are the adjacencies. Like, basically I'm copying the entire thing. But I'm going to keep group around because group is going to be important in a moment. Okay, so we've got that, Liberties for a group. So what I need to do is create the group. Let's come back down here. Comment all of this out. Actually, no, we won't. For test-driven development purposes, we're just going to do this. We're going to comment out that block of code, and then we're going to call self.stone adjacencies. Almost there, almost there. 167. Ah, yes. Some group. We're going to give it a we don't need to keep the group color any. Actually, we don't need to. We're not going to keep the group color. Yes, we are. That's useful. Useful information. Now we're going to give it a stone. We're going to do the same thing here. And that's both of those. Okay, individual liberties are being counted. Shared liberties are not. So now what we've got is a group which actually contains a stone, and the stone is a full value of its own. Let's make the group more capable. Let's turn it into a vector of stones. Okay, yep, you can't call adjacencies on a vector. Need to call adjacencies on each individual stone in the vector. So that means that group.stones.iter stone and so we're mapping. What do we get here? We're getting a list of lists. So we want to flatten that and take the length. And this should be something obscenely large for this group right here. No field stones on group. You're right. Fix that. And then the map operation, parentheses mismatches. Flatten, we will count it. And 241 and 190 are, okay, no, 241 is the incorrect line. And 241 is here in the adjacencies function. So actually what I kind of want to do is take all of this and put it right here. So self.stones, and then we're going to call come back to that in a moment. Group dot adjacencies dot count, and then we got to get this squared away. So max column, max row, and then we actually want to collect here. Not quite right. Well, what is line 187? Ah, I'm returning a vector, but still calling count. Count is only on iterators, call len on vectors. Okay. I think I forgot to write in the actual assertion for the number of adjacencies. I totally did. Assert EQ. Board.group at 44 dot map g board.group or board.liberties group should be sum 8, because that's what we counted earlier. And that should fail. It should be some much higher number. And gave me only 4. That's unexpected. Very unexpected. Oh, right. It gave me only 4 because I'm only putting the 1 stone in. Let's get all of the stones. We have to figure out how to make a group. And this, it's basically a recursive algorithm where I want to look, I grabbed a group of adjacencies for this stone, and I want to look at all of them and figure out if there is a matching stone next to it. But I don't ever want to backtrack. And there are algorithms that do this. I'm going to go back to our good old hex coordinates system, because this is a fill algorithm, actually. Hexagonal grids, still in my history. So, hex to pixel, conversions, neighbors, distances. It's distance, offset coordinates, line drawing, movement range. Given a hex center and a range n, which hexes are within n steps of it? Okay, this is it. This is not exactly it. Because this is actually just looking at a cube. There's obstacles. Here we go. Breadth first search, or distance limited flood fill. Is it reachable? Then we're going to add it. If we increase that, then of course we can see that more things are being added in. And I believe, let's see, fringes.append, for each hex in fringes, if the neighbor has not been visited. So it is actually, okay. So we're going to implement this. Might do it directly. Yeah. So let's see. I'm going to start a group right there. The group color, well, let's actually set up the visited set. Let visited equal hash set new. I'm going to have to go import that. Awesome. Okay. So hash set new and visited, it doesn't know what it's going to be. We'll just make each one a stone. We'll not make it a stone. We'll make it a coordinate. We'll make it an option stone. There we go. The first thing we want to do is grab the very first stone. Actually, let's work on this part. So let fringes equal a vec of column row, and it's going to equal nothing. And then fringes.append. I'm not actually going to do the fringes.append start here. I'm not going to do this line because I want to handle the first one specially. we're going to go ahead and grab the color. Actually, we're going to shortcut things. Here's where we get the match self stone. If it's none, then we're just going to bail. And we actually want to return that. If it is some, then we want to figure out the color and we want to save that off. Okay. Actually, maybe instead, I'll comment this out. Instead of using a match statement, we'll do an if block. So if let color equals self dot, if let some color equal self dot stone column row, else we will just return none. So the very first thing that we will do is we will create our group. And we're going to create it as let fringes.append visited. Interesting. Oh, I see. They're returning visit. In this algorithm, you return visited. Fringes is just where you're going to go looking next. I have to make both of those mutable, obviously. So we're going to start by adding the initial stone. Are we going to? No. Fringes.append. No, actually we are going to add the initial stone. Visited.add, I believe. Visited is a hash set. Maybe it's insert. It is insert. Okay. Back to our algorithm. Create a stone for this one with the color, the column, and the row. And then, actually, let's just create the stone. We'll call it the initial stone. I don't know that that's going to, that's not important. Let fringes equal stone.adjacencies, and then visited.insert stone. Not liking it. Oh, the only thing that's wrong is the return value. No, there's other things wrong. This expected two arguments. Self.size.width as u8 minus 1, self.size.height as u8 minus 1. There we go. Visited.insert. Insert exists for the struct, but its traits are not satisfied because a stone doesn't have the traits that are needed. Drive, clone, copy, debug, partial EQ, hash, probably also EQ. And it's expecting an option. We're not. We are. Yes, we are. think I'm overcomplicating it. Yeah, let's do this in 2 separate steps. Let's not do it in 2 separate steps. Oh. I'm trying to figure out how to represent the empty spaces because I don't really want to visit them again. And I think I'm not going to worry about it. I will need to work on optimizing later. Should be a U8, U8. Okay, so that's all good so far. Color is not hashable. Do I actually need it to be, do I actually need hash? Yeah, I do. Okay, so let's now I've actually forgotten which file I was working in. Types. I'm still in the correct file. Okay, a couple of warnings because things are not defined yet. Of course, I redefined fringes, which might not be great practice, but nevertheless. So now, we should have 4 elements in fringes. So for each, that part doesn't matter. What I want to do, so I don't know if you can modify an iterator while you're traversing it. So what I'll say is while fringes dot length is greater than 0, I want to, we'll just pop 1. So let column row equal fringes dot pop. Actually, I don't think while let, is this valid syntax? Let column row, or let some column row equal fringes dot first. Yes, that is valid syntax. Let stone equal stone. I want to keep track of the color in a very quick and easy way. So, oh, I've got the color. It's right there. If self.stone column row equals some color, then we want to do very similar processing to what we just did above. We want to grab the stone. We want to grab the fringes. I'm not going to do that. I'm actually just going to fringes.append the list of adjacencies. What does append expect? It expects another vector. I think maybe it's just not catching up. And then visited.insert stone. This pattern has, oh, got to get the syntax right still. That's a tuple that I'm destructuring. Good. Now, self.stone, the arguments are incorrect. How are they incorrect? That's, oh, these are references to U8s. There we go. And we're going to do that. unexpected identifier. Expected an identifier found a star. Oh. The shorthand doesn't work unless it precisely matches. Okay, now we're going to append. And append requires, theoretically, another list of vectors. So why is adjacencies not working? Expected immutable reference found struct vec. Oh, there we go. And I think I just ran infinitely. Right, I would have, because the stones are going to be, or the traversal is going to be bouncing back and forth between stones because I'm not actually checking visited yet. So, if visited dot contains stone, actually we're going to say visited dot, or if not visited dot contains stone, and we will do that. And now it should terminate appropriately. It does not. Oh boy, what am I messing up? Okay, I got to figure out how to not capture output. Rust cargo test show std out. Cargo test options, that's test threads, no run, no fail fast, target selection, feature selection, compile options, output option, no. Display options, no capture, that's what I want. Oh, wait, why is it just staying in the same place forever? That's a little weird. Fringes dot first. Oh, does fringes not first actually change? Rust vec. First. Oh, this doesn't actually, okay. The first operation doesn't actually modify the list. So we're basically just hitting the exact same element over and over again. Get isn't going to be the right thing. Maybe pop actually is the right thing. Pop is going to actually remove the element. Could remove from the beginning, but I actually don't care. Let's make sure that pop will return. It does return an option too. Good. I should have gotten tipped off by the fact that column and row are references. We need to be consuming the data. So yeah, that no longer works. This will get shorter. Here we go. Now let's run it again. And it's done. Cool. Okay. So we're returning none. That makes sense. Let's return some visited dot. This is a weird thing in Rust. There isn't really, I don't think there's just a method that goes directly from a hash set to a vec. Yeah, okay, so I will convert it into an iter, consuming it, and then I will collect it again. And that did not work. And because it needs to be a group. So this is a group with the color and with the stones being that. Not quite there yet. Expected struct stone found tuple. Oh. Yeah, these are not. Let's get rid of those lines and those. And 16, because we, why is that? Oh, right. It's because we're counting everything. We're not actually removing, or we're not really grouping them. So it's counting like all 4 of the directions on this one, and all 4 on this one, and all 4 on this one. Right. I knew that was going to be an issue. So what I actually think that I want to do next, now that I've got all of the stones, weirdly, I think I want to take the group, grab all of the adjacencies, and then remove those fields that have stones on them. So if we've got all of the adjacencies, take this out. And this should match. Good. Let's see here. To get the liberty count, I grab the group of stones that I grab all of the adjacencies for a group of stones. And I have the group of stones itself. So let's collect that. Oh. Okay, I'm going to do it in a way that's not actually all that elegant, but now that I've got everything in the adjacencies list, I'm going to into iter dot map coordinates. Actually, instead of mapping, I'm going to filter coordinates. The only ones that I want to allow through are the ones that are none. So board dot stone coordinates should be u8, u8. That's silly. Those are types. Column, row. Board dot stone column row dot is none. And then I'll count those. Self.stone. The arguments are incorrect. Again. Is this another... Oh. I'll just do that. And still failing. I'm still getting too many. I'm getting 10 on one of these. Looks like I need to reduce the number of test threads. just run them all one after another. Okay, so I still got a failure on that. I'm getting 10. I don't know why I'm getting 10. So I think that the only thing to do to solve this is to actually collect these and print them out. Okay, so for this group, 4, 3, so 0, 1, 2, 3, 4, 1, 2, 3. So that's 4, 3. So that means that this will be 5, 4 right there. And then we've got 4, 5. Is that really 4, 5? Where's 4, 5? 1, 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. That's actually 4, 4. It's counting all the way out here. That's not right. That's totally not right. Well, it's been over an hour. There's probably just some subtle bug in here that, I mean, there's obviously a subtle bug in here. Probably there's some ambiguities that are sneaking in right in here because I don't have a really great distinction between working with stones and working with addresses. Like maybe the entire adjacencies function should be a function on a tuple of U8, U8. That might be what I end up doing next. But in any case, I'm going to call the stream done here. And I'll keep working on this on my own, possibly get through a couple more of the tests. But I hope you found this informative. And I guess, yeah, I hope you found this informative. I hope to see you again next week. If you have any feedback, go ahead, drop me a message. You can leave it as a YouTube comment. You can find me on Mastodon and on Matrix. And thank you for watching. Sorry for the awkward close.